The story of our universe begins around 13.8 billion years ago with an event known as the Big Bang. Contrary to what the name suggests, the Big Bang wasn't an explosion in space. Rather, it was an expansion of space itself. At the moment of the Big Bang, all the matter and energy in the universe were concentrated into an incredibly hot and dense point, often referred to as a singularity. The cause of the Big Bang remains one of the greatest mysteries in cosmology. Several theories attempt to explain what triggered this monumental event. One possibility involves quantum fluctuations in a vacuum, where tiny, temporary changes in energy could have sparked the rapid expansion of space. Another theory suggests the Big Bang could be a result of a previous universe collapsing into a singularity and then rebounding in what is known as a Big Bounce. To understand the Big Bang and the early universe, we need to delve into the realm of theoretical physics. One of the key figures in this field is Albert Einstein, whose theory of general relativity revolutionized our understanding of gravity. According to Einstein's theory, gravity is not just a force between masses, but a curvature of space-time caused by the presence of mass and energy. This concept fundamentally changed how we view the universe and laid the groundwork for modern cosmology. Einstein's equations of general relativity describe how the universe expands and evolves over time. In the 1920s, the Belgian physicist Georges Lemaître applied these equations to cosmology and proposed that the universe is expanding. This idea was later confirmed by the observations of Edwin Hubble, who discovered that distant galaxies are moving away from us, indicating that the universe is indeed expanding. This discovery led to the formulation of the Big Bang theory. As the universe expanded, it continued to cool, allowing quarks, the fundamental building blocks of matter, to combine and form protons and neutrons. These protons and neutrons then came together to form the nuclei of the first atoms. This process, known as nucleosynthesis, occurred within the first few minutes of the universe's existence, creating primarily hydrogen and helium, with trace amounts of lithium. The conditions during this time were extremely hot and dense, similar to the interior of a star, allowing nuclear reactions to occur. As millions of years passed, gravity began to pull together the slight irregularities in the distribution of matter, forming the first stars and galaxies. These first stars, known as population Roman III stars, were massive and short-lived. They produced the first heavy elements through nuclear fusion and spread these elements into space when they exploded as supernova. These explosions were so powerful that they seeded the surrounding space with the elements necessary for the formation of future stars, planets, and eventually, life. Gravity continued to play a central role in shaping the universe. As galaxies formed, they began to cluster together under the influence of gravity, creating large-scale structures such as galaxy clusters and superclusters. Within these galaxies, smaller clouds of gas and dust collapsed to form new generations of stars. These stars went through their life cycles, fusing lighter elements into heavier ones in their cores. When massive stars exhausted their nuclear fuel, they exploded in supernova, scattering these heavier elements into space. Black holes, some of the most mysterious and fascinating objects in the universe, also formed during this period. A black hole is created when a massive star collapses under its own gravity, compressing its core to a point of infinite density known as a singularity. The gravitational pull of a black hole is so strong that nothing, not even light, can escape from it. Black holes can vary in size from stellar mass black holes, which form from individual stars, to supermassive black holes found at the centers of galaxies, including our own Milky Way. These supermassive black holes have masses millions to billions of times that of our Sun and play a significant role in the dynamics of galaxies. They can influence the formation of stars and the distribution of matter in their host galaxies through their intense gravitational pull and energetic jets. Observations of black holes have provided crucial insights into the nature of gravity and the behavior of matter under extreme conditions. The study of black holes also touches on the concept of Hawking radiation, a theoretical prediction by physicist Stephen Hawking that black holes can emit radiation due to quantum effects near the event horizon. Around 9 billion years after the Big Bang, in a galaxy known as the Milky Way, a cloud of gas and dust began to collapse under its own gravity, forming our Sun and the surrounding planets, including Earth. This process of planetary formation, known as accretion, involved particles colliding and sticking together, gradually building up a planet. The early Earth was a molten mass due to the heat generated by collisions and the decay of radioactive elements. Over time, the planet cooled and developed a solid crust. Volcanic activity released gases from the interior, forming the early atmosphere. As the planet continued to cool, water vapor condensed to form the oceans. These bodies of water played a crucial role in the development of life. The conditions on early Earth were harsh, with intense volcanic activity, a toxic atmosphere, and frequent impacts from comets and asteroids. Despite these challenges, life emerged in the form of simple, single-celled organisms. These early life forms began to change the composition of the atmosphere through processes such as photosynthesis, which produced oxygen as a byproduct. As life continued to evolve, it led to the incredible diversity we see today. Multicellular organisms appeared, followed by more complex life forms, including plants and animals. The evolution of life on Earth has been driven by a combination of genetic variation, natural selection, and environmental changes. As the universe expands, gravity has become weaker on large scales, but it remains a dominant force on smaller scales, such as within galaxies and solar systems. The interplay between gravity and other forces has shaped the universe in profound ways, from the formation of stars and galaxies to the development of planetary systems and the emergence of life. Understanding how the world was made requires looking back to the origins of the universe itself. The Big Bang set the stage, and through a series of complex processes driven by gravity, nuclear reactions, and the fundamental forces of nature, the universe evolved to form stars, galaxies, and eventually, our own planet Earth. The story of our world is a testament to the power of these forces and the incredible journey that has led to the existence of everything we see around us.